principle of mathematical induction.
Hi everyone, this is another episode of King Solomon and David Picosi on algebra. So today I'll be dealing with the principles of mathematical induction and principles of mathematical induction. Now, under inductive reasoning and under relative reasonings, that's the logical reasons and other stuff, there is something we call a conjecture. A conjecture. So a conjecture is something like, it's more or less like dealing with formulas, how you can prove that a formula is true or not. So with mathematical induction, you just want to prove that a relation which involves a formula makes the formula valid. So a relation which involves a formula makes the formula valid or not. Okay. And these are one or two procedures or we are supposed to take note to prove the validity of that particular formula in mathematical induction. So first of all, you have to prove the statement for n equal to 1. So n equal to 1 means you have to prove the statement whether it is true for the first term. So you have to prove the statement whether it's true for the first term anytime you are given such a relation. Again, you have to also assume that the statement will be true for some induced value k, where k is any positive integer. So you assume that the statement is true for some induced value k. After doing that, you have to also prove that that statement is also true for some other positive values, which is k plus 1. So addition of 1 to the k. Some other positive values, which is k plus 1. Now, when you're able to do that and the assumption is true for all positive integers, improving the validity of the formula, then the assumption is now or the axiom of mathematical induction. So it's more or less like you are inducing some value k into a relation to prove the validity of a formula. Let's take about 2 or 3 examples and let's look at how we can do it. So now we use the mathematical induction. We use the mathematical induction to prove it. So before we come to the examples, there are 2 things you have to note here. So the procedure we use, first of all, we use 2 conditions. So from this, the conditions we can write here is 2 conditions. So the first condition is that you should prove the initial value, the first term. And if this is true, we can now move on to the next condition, which is the inductive condition. Now, with the inductive condition, you have to now assume a certain value of k. Now, if you assume the value of k and the statement is still true, so this assumption you are doing here is what we call the inductive hypothesis. The inductive hypothesis. So under the inductive condition, we first do what we call the inductive hypothesis. So after the inductive hypothesis, if it is true, then we move on to put a certain value, prove that n is equal to k plus 1. So when you prove that n is equal to k plus 1, then you can say the formula is valid. Okay, so let's take our first example. And let's look at it. So the first example is that you should prove that 2 plus 4 plus 6 going on to 2 plus n is equal to n into bracket n plus 1. Okay, so this is the relation we have been given here. And we have to use the principle of mathematical induction to prove the validity of this. Now, how do you go about it? The base condition. So now we have to assume the first n term. So what is the first n term over here? It's 2. So now if n is equal to 1, if n is 1, so the solution is, so now if n is 1, will this be valid? So if n is 1, coming to the right hand side here, we have this is the equation. So let's start. This is the equation or the formula n plus 1. N into bracket n plus 1, which will go for these all things. Okay. So now if n is equal to 1, in the first instance, you prove that the statement for n is equal to 1 is true. If n is equal to 1, Then in the formula, 1 into bracket 1 plus 1 will give you what? That is 1 times 2, and that is 2. So realize that if n is equal to 1 and it gives exactly as the first thing in the series, then it's true. So that means here for n is equal to 1, it's true. Now we can now move to the inductive case. So with the inductive case, we can now do the inductive hypothesis. So now let's put if n is equal to k. So if n is equal to k, we get 2 plus 4 plus 6 plus 2 of k, which is equal to what? K into bracket k plus 1. And that is the same thing. So if n is equal to k, then the inductive hypothesis is also true. So this is the same k. It's like the replacement of k. Now, the third thing is when we have, if this is true, then we should prove that n is equal to k plus 1. We should prove that n is equal to k plus 1. So n is equal to k plus 1, we have to check this side first, and after we come to check this side. So we check this side first, and we come to check what? This side. So now, n is equal to k plus 1 simply means that we have to add an expression of k plus 1 of the last digit, an expression of that to each of the sides. Okay, so now what happens is that if n is equal to k plus 1, we have 2 plus 4 plus 6 plus 2k. So now the next expression, because k plus 1 means you are going to the next expression. And now here is the one that's like, the difference here is 2. So the next expression, if n is equal to this, the next expression that we add is 2n. So that becomes what? 2 into bracket k plus 1. I get it. So that will be the next expression, k plus 1, equal to this side of the equation, which is also what? Which is also k. So we are putting the n is equal to k plus 1. So here is n. The n here is what? K plus 1 into bracket. Here is also what? K plus 1 plus 1. Okay. So now what happens is that the left hand side should be equal to the right hand side. If it is equal, then the formula is valid. Okay. So what do we do here? The whole of this, from here to here, is what was given in the inductive hypothesis. And that was equal to k into bracket k plus 1. So we can just simply go k into bracket k plus 1 plus 2k plus 1, which is equal to k plus 1 into bracket k. This one is 1 plus 1, that will be plus 2. Okay, so realize that here, factorization, the things in the bracket are the same. So we get k plus 1, and these ones are out, which is k plus 2. I get it. So k plus 2. So if you do this is what you are getting, which is equal to k plus 1 here, multiplying with what? K plus 2. So since the right hand side and the left hand side are equal, then we say the equation n plus 1, n is valid. So 2 plus 4 plus 6 giving 2n here, n plus 1 is now valid. Okay. Let's take our second example. Okay. So our second example says that we should prove that 1 plus 2 plus n is equal to n into bracket n plus 1 all on 2. 1 plus 2 plus n is equal to n plus 1 all on 2. Okay, so now since you know this is the formula, n plus 1 on 2. So solving, if n is equal to 1, will we get the first thing? Let's see. So we get 1 bracket 1 plus 1 on 2. So this will give you 2 on 2, which is equal to 1. So we are getting the first thing over here in the series, so it is true. Now if that is true, our inductive hypothesis, if n is equal to k, is it true? So we have 1 plus 2 plus k should be equal to k into bracket k plus 1 all on 2. And that is also true. So our inductive hypothesis is also true. If our inductive hypothesis is true, then we put if n is equal to k plus 1. So that means our next thing, if n is equal to k plus 1. So it's more or less like we are now putting this our next thing. So we get 1 plus 2 plus plus k plus 1. So that's our next thing, which is equal to here. So n is what? Now k plus 1 into bracket k plus 1 here. Sorry, plus 1 all divided by 2. So now if you solve for this part and this part and they are getting the same answer, then they are valid. So now what you can do here is that you realize that the whole of this is what we see here. So therefore the whole of this can be k into bracket k plus 1 on 2 plus k plus 1, which is equal to k plus 1, and here it gives you k plus 2 all on 2. So you have to solve this side and see whether it's conveys to this side. So breaking this down, we get k squared plus 3k plus 2 all divided by 2. And when you solve this, you are getting, if you find the quadratic equation, the root, you are getting k plus 2, k plus 1 all on 2, which is the same as k plus 1 here, k plus 2 here, all on 2. So this being right means that the equation is what? Is valid. Okay, so we're still with examples. I want us to solve last example under the mathematical induction. And the example says that we should prove that for all integers, that's n greater than 3, this formula holds. 2n should be greater than n plus 4. Okay, so this is the example I want us to, the last example I want us to solve. So now, going through the conditions. So the first condition says that we should take the first thing. So now, if you take n is equal to 3, what do we get? You get 2 raised to the power 3 should be greater than 3 plus 4. And if you do this, you are getting 8, which is actually greater than 3 plus 4, which is 7. So that means the first thing is true. So now, with the condition 2, which is the inductive hypothesis. So the condition 2, which is the inductive hypothesis, we put n is equal to k. So if n is then equal to k, then 2 of k should be greater than k plus 4. And this is also true. If this is true, then the actual inductive condition says that we should put n is equal to k plus 1. So if the n is equal to k plus 1, then we have here to be 2 plus, we put k plus 1 here, should be greater than this part, which is the k plus 1 here, plus the 4. So now we have to make sure that the left-hand side will actually be greater than the right-hand side. So how do you go about it? So now with the left-hand side, we have 2k is indices, dot 2 exponent 1. So now what do we get from the left-hand side here? We realize that 2k is already greater than k plus 4. So that means the 2k here can now be k plus 4 multiplying 2, which is the same as 2 into bracket k plus 4, giving you 2k plus 8. Now, the right-hand side, so this is the left-hand side. Now, with the right-hand side, what are we getting? We are getting k plus 1 or plus 4, which is the same as what? K plus 5. Okay, so now when we come here, you realize that the left-hand side, which is 2k plus 8, is actually greater than k plus 5. So if this is also true, then the formula holds for all integers when n is equal to 3 or n is greater than 3. So it makes the formula 2n greater than n plus 4 valid. Okay, so thank you guys very much for joining me on the principle of mathematical induction. Let's move on as we journey through algebra from King Solomon and David Pecosi on this particular platform. Thank you.